So we'll take another one on path sensitization. Um, we are trying to detect faults in this circuit. So you realize it's quite a huge circuit, and you were given that you had to find the test vectors for A stack at 0 and B stack at 0 as well, using any of the path sensitization algorithms. So let's get to work. So that the whole routine it's not confusing with the numbers. Let me label the input instead of numbers. Let's use letters. Let me call this A. Let me call this B. Let me call this C and this D. Okay. So that instead of numbers, we have letters. Now, um, for A stack at 0, right? We have to make sure that whatever is coming to this point, because this is the point of the fault, we have to do for A stack at 0 before we come and do B stack at 0. Assuming the fault did not occur together. Okay, so for A stack at 0, you have to assume that this point, whatever is coming here should be 1, right? So that we can activate the fault, because A is stuck at 0. So to be able to activate the fault, you have to make sure whatever is coming there is 1. Now let's call this gate 1. Okay, so if um gate 1 has to output 1, then it means that B has to be 0, because that's the not gate. Okay, and if it's outputting 1, B has to be 0. And this is under the assumption that um only one fault occurs in the circuit, like there's no multiple faults in the circuit. Okay, so it means that, let's say B is at 0. Okay, that's the only way Gene will output 1, and we can activate the fault A stack at 0. Then what we have to do is that, you see, we are supposed to find the test vector. So the thing is, we are supposed to propagate this error forward. We are supposed to propagate this error all the way through the circuit up to the outputs. Okay, and that's the main challenge here. So in propagating this error forward, we have the erroneous inputs at this point is feeding into this NAND gate and this AND gate. Okay, so to be able to send this forward, then it means that we have to make sure that the output depends on the erroneous input, so that we can see its effect on the outside. Okay, so if the output is supposed to depend on it, then it means that we have to make sure that the input C, right, coming here is always 1. Okay, now here is the reasoning. Although it's just an assumption as at now, we are assuming that we are making the error take this path. You see, the error could have taken this upper part and gone, but we are trying this lower part before we try the upper part. Any one which results in any inconsistency will revert back and move on to the previous the next one. So in order to do that, then let's make sure that C is 1. Okay, so if C is assumed to be 1, then the erroneous input A would appear here. Okay, so it means I'll have some kind of A here. We just want any term containing A that we can test for, so some kind of A. Now if C was 0, the output will always be 0, so we can't really test for A stack at 0. That was the reason why we are doing this. Now here at the upper part, you realize that at this point we have a NOR gate, right? So if you have any NOR gates, assuming that the NOR gate, the inputs of a NOR gate are X and Y, right? So the function for a NOR gate is what? X plus Y or bar, right? Now you realize that this circuit, let's assume we want the circuit to depend on X, right? Then it means that we have to push Y to 0, okay? So that the circuit will reduce to something like X bar. We want some kind of a single variable term, okay? And that's the same thing we do here. So here we have A coming, and we have we want the circuit to depend on only A, right? So it means that we have to find some way somehow to make sure that this gate, let me call it gate 2, right, is always outputting 0. Okay, just like the white term here. So if gate 2 is always supposed to output 0, right, gate 2 is a NAND gate, right? And a NAND gate, and I'm using the same analogy. In a NAND gate, if you have x and y as the input, then you have x, y, or bar. Okay, now to be able to get 0 for a NAND gate, right, all you have to do is to make sure that both of the inputs are 1, right? Because if any of the input is 0, you get 1, right? You can try it. So both of the inputs have to be 1, right? So the inputs are first this A, right, and second this capital A as well, right? Now it means that we have to set this capital A to 1, right? And this A shouldn't worry as much right now, because you're assuming that for whatever case the output of the gate is 0, right? Although if you're not really sure of it. So if the output of that gate is 0, then it means that you have 0x or something, so you can get some kind of A bar here. Okay, this is not all, sorry. Then here you have C being fed into D, being fed into an XOR gate with D. But the truth is, the function becomes what C XOR D, and this function, when you make C a constant 1, because of our assumptions, if C is a constant 1, then you get I mean, the function is generally this way for an XOR. So if C is a constant 1, then you get D bar. Okay, and you are just feeding into this end gate, right? Now, so that A doesn't A is the one which is changing the output, means you have to fix the output here towards 1. So it means that we have to assume this gate, let me call it gate 3, is always outputting 1, right? And to be able to do that, given our conditions, then it means that D has to be what, 0, so that D bar will be 1. And that would bring us to the edge. So you realize that in this case, the test vector is A has to be 1, B has to be 0, C has to be 1, and D has to be 0, 2. Okay, and that's one direction. So let's try the same thing from the flip direction. I think the first one, the test vector was 1, 0, 1, 0. So let's try the same thing for the flip direction. In the flip direction, at first we were trying to use this part. So now let's use the upper part. So in the upper part, it means we are trying to get something like A here. Now, when you look at the diagram, this is the NAND gate, right? So that A would propagate here, then we have to make sure that this capital A is always set to 1, right? It's always set to 1 because it's a NAND gate, right? In a NAND gate, when any of the inputs goes to 1, then the other one has to be determined before we can determine the output. But when any of them goes to 0, the output will always be 1, right? Which means we can't determine which one was 0 or which one was 1, right? So it means that we have to make sure that it's a NAND gate and A is 1. So capital A is 1. Then which means that at the output we have A bar. And it doesn't matter whether we have A bar or A. All we want to do is at the end of the day have A at the output, like propagate through the circuit to the output. so that we can do our determination. So once we have it here, you realize that this is a NOR gate, okay? And in a NOR gate, assume you have, it will be something like X or Y or bar, right? Now let's assume that we want it to depend on X. It means that Y has to be what? 0, because if Y is 1, then the whole circuit will always go to 0. Okay, so we always want one of them to go to 0, and it means that we have to let the lower one go to 0. So this circuit is assumed to be always 0. Okay, now if this circuit is assumed to be always 0, then at the end of the day, what will propagate here is what? A, right? Because it will be A bar bar. Okay, so A. Then now we come to our next branching point, and we have an AND gate. Okay, and in an AND gate, to ensure that this gate allows only A to propagate, or A determines the output, then it means that we have to set here to 1. Okay, yes, and when we set here to 1, then A will come to the output. Now, to determine what the exact inputs were, then we have to propagate backwards. Okay, so in propagating backwards, we realize that this circuit here is supposed to output 0. Okay, now at the top, it has A, which we don't know, so we don't really want to deal with it now. But I realize that if we set the down to 0, then this whole circuit will always produce 0. So why not make C 0? Realize that in the first one C was 1, but this one C is 0. Okay, so if we set C to 0, it works, right? And now realize that A was stuck at 0, right? According to the question. So to be able to test for it, it means that we have to produce a 1 here, okay, to activate the fault, which means that B has to be what? Set towards 0. Okay, and now this whole circuit is a 1, right? And this circuit is supposed to produce a 1, right? And we've already determined that what C is 0, right? Through the back propagation method, C is 0, and it is it's a XOR gate. Okay, so the that how do you call it? The Boolean function is something like this. Now, if C is 0, then it means that D has to be 1. Okay, to ensure that the output is 1. Okay, and that's what you get. So you realize that in the second case, the test is what? 1001. Okay, so 1001. Now, which one to choose? Well, you realize that in the very first one, right, we had a bit of a problem determining what the A should be when we were propagating backwards, right? But the second one is more sure, so I believe that we can go with the second one, right? However, let's still try the Boolean difference method to check if we'll get the same answers. Okay, so for the Boolean difference method, it says that any of these circuits can be represented as f of, given that y is 0, x, or f of, given that y is what, 1, it's supposed to give you 1. What it's saying is that when you test the circuit with the fault against the circuit without a fault, right, if there's truly a fault in the whole circuit, then you should get 1. Okay, so that's what we are going to do. Now let's write a Boolean function for this whole circuit. Okay, and I'm pretty sure you can do that by now. Okay, so realize that at the top here you have A and B bar, because the B is going through an inverter, so A and B bar feeding into an an NOR gate, and you have B bar and C feeding into the NOR gate. Okay, so let's write it down. So you have A and B bar they were NAND, then they were fed into a NOR gate with what B bar and C. So plus B bar and C, and it was a NOR gate, so all the expression has to be NORed. Then, so we've done for all these big ones, right? And this one is ended with the bottom one. So let's draw the symbol. So when it's ended with the bottom one, you have C XOR D. That's what will appear here. So you have C XOR D, right? And so this will be our total function. Okay. Now, where is small letter a? This a in the question. Well, remember that this a in the question is just coming from. So I think we realize it. A is B bar. Small letter a is B bar. So anywhere we see B bar, we can put small letter a there. Okay, so let me try. That means that this equation can be rewritten as the bar on top. Then you have capital A, small letter a, all bar plus small letter a multiplying C, then C XOR D. Okay, and yeah, now the next part is we have to put small letter a equals to 0 and small letter a equals to 1 into the equation. So if small letter a is equal to 0, right? I don't want to write plenty, but when small letter a is equal to 0, realize that this part will go away, right? And this one would become 1, right? So this outside expression will become 1 complemented, so 0. So 0 multiply the whole expression. So this one will become 0 if a is equal to 0, right? Then this whole big expression would also go to 0. Okay, yeah, because when a is 0, this one becomes 0. Fine. Now this one becomes 0, making this first bar 1, but this second bar will complement it to 0 and multiply the whole thing again. Now if small letter a is equal to 1, shit, trouble. Okay, if small letter a is equal to 1, then realize that this c will remain and this a also remain. So we'll have something like this. We'll have capital A bar plus capital C all bar multiplying C XOR of what D. Okay, yes, so that is what you will have. And the next steps are you have to determine the values for which this function would give you 1. No, sorry, we are not done yet. So this is um, when a is equal to 0, you have a 0, and when a is equal to 1, you have this expression. Yes, so you have to determine the x of the two of them. So when you have 0 XOR this expression is long, so 0 XOR this expression C XOR D. Right, now what you realize is that the results of this one will just come to be the same expression. Okay, so A XOR C multiplying C XOR D. So you have to find values for which this function will be equal to 1. Okay, and one thing is for they are multiplying, right? They are AND gates. So it means that this whole thing has to be 1 and this whole thing has to be 1 so that the whole function goes to 1. Okay. So one of the shortest ways that realize that C, X, or D will only be 1 if either of them is 1. If both of them are 1, you will get a 0, which will make the whole function go to 0. So it means that if C is equal to 1, D has to be 0. And if C is equal to 0, D has to be 1. So those are the possible values for this one. Now, for A bar plus C or bar, you have to check. The function under the bigger bar has to be always 0. Okay, so that it will be inverted to 1. Okay, so that when you multiply the whole expression, you get a 1. So you realize that when A is equal to, when either A or C is equal to 1, you get a wrong answer. So you have to make sure that either of them is always 0. So it is either A is equal to 1 and C is equal to 0, or you have an expression such that A is equal to, yeah, I think that's the only expression. In both cases, A has to be 1 and C has to be 0. Else, all other possible combinations would bring this side to 1 and the whole thing to 0. So I think that's the best combination. So 1 0 again. So you realize that when you match them, it's either you have 1 0 1 0 or 1 0 0 1. Right? Those were the two possible cases. And you realize that those were the two possible cases we had here for our um, part sensitization method. So either of them do give 1001. So I think it will depend on the one which does not bring any form of inconsistency during the backward propagation step, right? And so I think it's just the 1001.